Welcome to the Explainer. Today we're strapping on our hard hats and heading straight into the ultimate engineering challenge. I'm talking about the truly monumental task of digging through our planet's most unforgiving environments. Picture this, massive tunnel boring machines, or TBMs, just grinding through raw earth, with towering mountains looming in the background, and the deep dark sea pressing down around you. It's an environment completely defined by heavy construction, grit, and honestly, constant palpable danger. Every single operation is a literal battle against the elements. So how exactly do we engineer paths through solid granite and beneath billions of gallons of water without the whole shebang collapsing on top of us? Well, let's find out.
How do we survive the dig? Before we even look at the engineering side of things, we really have to ask that fundamental question. How do crews even survive this? When you step into a subterranean dig site, you're stepping into a place where the very earth and sea are actively bearing down on you. The background is just loud, dirty, and incredibly perilous. Every time we venture beneath the crust or the seabed, we're placing ourselves directly in the crosshairs of nature's immense weight. Surviving this kind of dig requires absolute precision, highly specialized machinery, and this constant hyper-awareness of the environment closing in around you. There's literally zero margin for error when the ground itself is trying to reclaim the space you're carving out.
Mountains with solid rock and unpredictable faults versus oceans with crushing water pressure and soft sediment. Comparing these two environments reveals a crazy dual challenge for engineers. Up in the mountains, you're battling solid rock and hidden, completely unpredictable fault lines. These faults are incredibly dangerous because they can shift without any warning whatsoever, creating this uneven pressure on the drill heads of the TBMs. And that can suddenly snap those massive cutting discs right off. It's a highly volatile environment. But then, under the ocean, the dynamic completely changes. Instead of hard rock, you're often dealing with soft, shifting sediment. So you have two completely different construction backgrounds, both incredibly hazardous if you miscalculate even slightly. The mountain threatens to break your equipment to pieces, while the ocean threatens to just swallow it whole.
Tunneling, the perilous engineering process of excavating a subterranean passage through mountains or beneath oceans. I want you to really focus on that word right there, perilous, because obviously this isn't just digging a hole in your backyard. This is a highly calculated, heavily mechanized invasion into environments that simply do not want us there. It's a constant minute-by-minute battle against nature's absolute extremes, where heavy machinery and brilliant engineering are quite literally the only thing standing between success and utter catastrophe. Every single cubic meter of removed earth is a hard-won victory against geologies that have been locked in place for millions of years.
The crucible, man versus nature. You really have to think of the construction process as a crucible. It's this definitive test of human limits against the raw, unyielding danger of the earth. When a crew is miles deep into a mountain, surrounded by the deafening roar of excavators, they are in that crucible. Down there, the heat generated by the intense friction of the drill bits against rock is absolutely sweltering. You need these incredibly complex ventilation systems strictly just to pump in breathable air and flush out toxic dust so the workers can actually survive. Because here's the thing, the mountain and the sea, they're entirely apathetic to our presence. They just want to collapse back into their natural resting state. We're the ones forcing them open, defying natural law with sheer mechanical willpower.
Let's look at mountain challenges, extreme rock density, hidden fracture lines, and unpredictable cave-in risks. Just notice the gritty reality of mountain digging here. Every single inch is fought for, violently, against solid rock. That extreme rock density just destroys drill bits and pushes heavy machinery to its absolute breaking point, which requires constant, expensive maintenance. And those hidden fracture lines mean that a seemingly solid wall of rock can just suddenly compromise the entire structural integrity of the tunnel. Because of this, unpredictable cave-in risks are basically the shadow hanging over every single worker in that tunnel. It's a harsh, jagged environment where safety is never guaranteed, and you have to run constant geological surveys just to anticipate the next catastrophic fracture.
Now, on to ocean challenges. Immense water weight, shifting soft sediment, and the constant threat of total inundation. Contrast the mountain with the ocean depths. Here, the danger shifts from the violent cracking of falling rock to the terrifying silent force of hydrostatic pressure directly overhead. The massive weight of that water column is just constantly looking for a way in. When you're excavating through shifting soft sediment under the seafloor, stability is incredibly hard to find, precisely because that muddy earth lacks any self-supporting strength at all. So the ultimate nightmare here isn't necessarily a falling rock. It's the constant threat of total inundation. Just a single breach, literally a microscopic failure of the tunnel walls, and the ocean will rush in with an unstoppable force, flooding the entire system in a matter of seconds. So we have 3 steps here. 1. Survey the unpredictable extreme terrain. 2. Excavate through massive physical resistance. And 3. Immediately reinforce to prevent collapse. Surviving these 2 extremes really relies on this precise choreography. There's a rigid methodology to staying alive down there. Step 1. You survey that unpredictable terrain. You're using seismic waves and probe drills to know exactly what's coming before the main cutter head even hits it. Step 2. You excavate through massive physical resistance, just using sheer mechanical force. But Step 3 is where lives are saved. You immediately reinforce to prevent collapse. You can't just dig and leave the space empty. The exact second the rock or sediment is removed, immense automated arms must swing right into action, locking these massive precast concrete segments into place to form a permanent ring. Survey, dig, secure. It's the steady heartbeat of subterranean construction.
Millions of tons hanging just inches above. That is the crucial reality of this job. Whether it's a dense mountain range or the floor of the sea, that unimaginable mass is held back only by the immediate reinforcements the crew just installed. Often, they're using specialized shotcrete, which is this fast-drying concrete sprayed at high velocity to stabilize the raw rock instantly. It requires an incredible amount of psychological endurance to operate heavy machinery in a confined space where the natural world is actively trying to flatten you. The sheer scale of the geology up above is constantly testing the limits of the steel and concrete down below.
And that brings us to the phrase, under mountains and oceans. This really perfectly underscores the absolute extremes of the locations chosen for these massive engineering projects. I mean, we don't just build tunnels where it's easy or convenient, right? We build them where they are desperately needed, which inevitably means diving beneath the most intimidating geographic features on the planet. It's a testament to the sheer audacity of modern engineering that we can look at a towering mountain or a vast, unpredictable sea and confidently decide, yep, we're going right through it. The logistical nightmare of deploying a specialized workforce into these remote, hazardous zones is a monumental feat all on its own.
The danger of the dig. You can just feel that danger down here. It's palpable. Just imagine the showers of sparks as massive rotary blades hit a pocket of solid granite. You can almost smell the pulverized dust in the air, hear the deafening echo of heavy machinery in a confined space, and feel the atmospheric tension of an active, highly hazardous tunnel construction zone. Everyone down there knows the stakes. The entire background of their daily work is this intense landscape of jagged rock, immense pressure, and the ever-present hum of industrial equipment keeping the formidable forces of nature at bay. It's just this incredibly high-stakes ballet of steel, earth, and human resilience.
Connecting an unforgiving world. Ultimately, we take all these massive risks for one fundamental reason: the relentless human drive to connect our world. We don't dig just to dig. We push through the most dangerous natural obstacles in existence because we need to move people, goods, water, and power efficiently. We're connecting cities separated by impassable peaks and continents divided by treacherous waters. The extreme danger of the construction zone, the staggering costs, the grueling labor, it's all the price we're willing to pay to conquer geography and bring an unforgiving world just a little bit closer together.
So, what are the ultimate limits of human engineering? It leaves us with this final lingering question. As our technology improves and our need to connect grows exponentially, what really are the limits? If we can confidently hold up millions of tons of mountain rock and hold back the terrifying depths of the sea using massive boring machines and spreed concrete, how far and how deep will we eventually go? It's a striking reminder of the extreme, perilous lengths we'll go to conquer the earth and sea. Thank you so much for joining me for this explainer. Keep asking questions and keep exploring.